Good morning, welcome to new lecture in the unit of random process, and today in this lecture we will continue our discussion about Gaussian processes. So, let us first recap the main ideas that we discussed in the last lecture. So, here comes the first big idea that we discussed. So, we said that if we have m IID normal random variables, so W1, W2 and Wm are m normal IID random variables, and if I make different linear combination of these normal IID random variables, then what I end up with are jointly Gaussian random variables. So, Z1, Z2 and Zn are jointly Gaussian random variables. So, we have defined jointly Gaussian random variables as the random variables which are obtained by different linear combinations of common underlying set of normal IID random variables. Also note that even though we have been developing our model assuming these W1, W2 and Wm as normal IID random variables, but we could have also assumed them to be independent and Gaussian. Okay. This assumption is just for the simplicity. Okay. So, that is one big idea that we have seen in the last lecture. We have also looked the second way of defining these jointly Gaussian random variables, and this is that if and only if any linear combination of random variables. So, these Z1, Z2 and Zn are random variables, and if any linear combination of these random variables leads to a Gaussian random variable. So, Y1 has to be a Gaussian random variable, then the underlying random variables are jointly Gaussian random variable. Okay. And we have also seen the equivalence between the first definition and the second definition. Okay. So, this is for jointly Gaussian random variables. We have also defined Gaussian process, and what is a Gaussian process? So, first Gaussian process is a random process, and we know that a random process can be understood by taking samples of this random process at different time instance. For example, we have taken the samples of this random process at time instance t1, t2 and tn. Once you sample a random process at different time instance, we end up with different random variables. Okay. So, in this case let us say we have obtained n random variables, and if these random variables are jointly Gaussian random variables, then the underlying process is a Gaussian process. Thus, we can define Gaussian process as a process whose samples are jointly Gaussian random variables. Okay. So, a lot of definitions flowing in. We also defined Gaussian random vector. So, what is a Gaussian random vector? It is a vector whose elements are jointly Gaussian random variables. So, for example, here Z is a vector and the elements of Z are Z1, Z2 and Zn, and as we have already seen that these are jointly Gaussian random variables. So, that is a Gaussian random vector. We have defined the covariance of a Gaussian random vector, which is given by expected value of Z into Z transpose. Remember that in last lecture and in today's lecture we always assume random variables to be with 0 mean, and if these random variables are with 0 mean, then the covariance of this random vector Z can be simply obtained by carrying out this expectation operation. And what we have also showed that this is nothing but A into A transpose, and what is A? A is the matrix with which we were multiplying this vector W to get vector Z. Okay. So, this is one idea that we will also use, that the covariance of a Gaussian random vector is nothing but A into A transpose. Okay. Then we were trying to derive the probability density function of this random vector Z, and what we have said is that the probability when you go from W space to Z space will be preserved, and probability can be thought as multiplying the probability density function with the volume. So, the probability in W space is the probability density function in W space multiplied by the volume in the W space, and this is the probability in the Z space, and these probabilities must be same, because every point in W space is mapped to a point in Z space. Thus, the probability of finding a point in W space would be same as the probability with which you will find the point in the Z space, where the points are the map of the points of the W space. Okay. This we have seen in the last lecture in a lot of details, right. And from this we derive that the probability density function of random vector Z can be obtained in terms of probability density function of random vector W divided by mod of determinant of A. We have also seen that determinant is nothing but it is the volume scaling factor which describes the linear transformation. Okay. Okay, so we will start today's lecture from here. Let us rewrite some key equations that we have seen in the last lecture. So, first key equation is Z is A times W, and the probability density function of random vector Z is probability density function of random vector W divided by mod of determinant of A. Okay. And we have already derived the probability density function of this random vector W. So, probability density function of random vector W, this is also what we derived in the last lecture, is this thing. Okay, where m is the number of elements in this vector W, and we have also seen that this is norm square of vector W, and we know that norm square of any vector can be thought as sum of squares of these elements W1, W2 and Wm are nothing but the elements of vector W. Okay. So, this is how we can think about norm square of a vector. Okay. So, let us now, so this is what we have seen in the last lecture. Now, let us try to develop few more equations. So, starting from Z is A times W, I can multiply this with A inverse. So, multiplying with A inverse on both sides, and what we are assuming is the inverse of a matrix exists. Okay. So, first thing is A has to be a square matrix. And thus n should be same as m. Okay. And we will see that even if A is a square matrix, there can be a case when inverse does not exist, but let us assume at this moment that the inverse of this A matrix exists, and let us also assume that A is a square matrix, okay, where n is same as m. Now, we know that if the inverse of a matrix exists, then A inverse times A is nothing but identity matrix. Okay. So, we can say A inverse times Z is I times W, and identity times a matrix is nothing but the matrix itself. So, we know that W vector is nothing but A inverse multiplied by Z. And now, what we want to do is we want to find out the probability density function of Z in terms of probability density function of W. And we have seen that vector W is nothing but A inverse times Z. So, numerical value of this vector W would be same as A inverse times small z, where small z denotes that it is the numerical value of vector Z. So, what I mean with this is Z would be nothing but some vector with some numbers. Okay. So, it denotes the Z1, Z2, Z3 and Zm are some numbers, and Z is also a numerical value consisting of m numbers. Okay. And this Z is a random vector. This Z is a vector which contains some numbers, right, as we have seen in the case of random variables, that x is a random variable and small x is the numerical value of that random variable. Okay. So, if I know that W is A inverse times Z, we had norm of W square, and norm of W square would be same thing as this. Okay. Now, what is this norm of W square? We have already seen that this is nothing but W1 square plus W2 square up to Wm square, and all these W's are small w's. Okay. And this is nothing but W1, W2, Wm multiplied by W1, W2, Wm, and this is what? This is W transpose and this is W. So, remember, as I have already said, that the vectors are always assumed to be column vectors. So, this is a row vector, so it has to come with a transpose. So, this is W transpose times W. So, what we are saying is simply that norm square of W is nothing but W transpose times W. Similarly, norm square of A inverse Z is nothing but A inverse Z transpose times A inverse Z, and this we can solve using properties of matrix. This will be Z transpose A inverse transpose A inverse into Z. Now, we have already seen that the covariance of this random vector Z is nothing but A times A transpose. So, the inverse of this covariance matrix is A transpose inverse. Okay. Now, this is simply A inverse transpose times A inverse. All this follows from the properties of matrices. Okay. So, if you have forgotten about them, it is a good idea to have a look to these properties. And now, something interesting has happened. We have this term here. So, this is nothing but inverse of covariance of random vector Z. So, using this idea, what we can say is nothing but, so we have Z transpose K Z inverse times Z. So, that is one equation that we will use. Second thing that we want to see is that K Z is A transpose. So, determinant of k z is nothing but it is determinant of A transpose, and this thing is same as determinant of A into determinant of A transpose, and determinant of a matrix and its transpose is same. So, this is determinant square of A and so determinant of A will be plus or minus square root of determinant of k z. So, this is the second equation that we will use. So, now let us see what we are up to. So, let me rewrite some equations. So, we have said that probability density function of random vector W is and we know that the probability density function of random vector Z would be this probability density function divided by mod of determinant of A into exponential of this thing. And now we have developed two equations, that determinant of A is nothing but plus or minus square root of determinant of k z. So, mod of determinant of A is square root of determinant of k z, that is one thing. Second thing is, we have seen that norm of W square is nothing but norm of A inverse Z square, and we have proven this is simply Z transpose k Z inverse times Z. So, what we are up to is we are trying to express this probability density function in terms of Z. So, we want to get rid of W, okay, because this is a function of Z. So, we want to talk in terms of Z rather than in terms of W, right. So, the final expression for probability density function of Z will be and this is an important result. So, we have been able to derive the probability density function of random vector Z, and remember that this random vector Z is actually a Gaussian random vector. Okay. So, now we have the probability density function of a Gaussian random vector at our disposal. There are few things that are interesting here, that this probability density function is completely specified by this covariance function, right. So, it is an important idea, this probability density function is just a function of k z, right. So, if you know k z, you can completely specify the probability density function of Gaussian random vector. Thus, a probability density function of a Gaussian random vector is only dependent on its covariance matrix. Okay. So, in this expression what we have assumed is that this random vector is with 0 mean. Let me write the expression of probability density function which will be when this random vector has some mean. So, let me first write and then we will discuss about this. So, the probability density function of this random vector z when this is not with 0 mean will be simply so what we see here is, what is this mz? Mz is the mean of random vector z. Okay. So, now if this z is not with 0 mean, the probability density function depends upon two unknowns. One is this covariance matrix and then the mean, right. So, if z is not 0 mean, then this probability density function is a function of mz and kz, but overall this probability density function will only be a function of these two variables, right. Once you know the mean of a Gaussian random vector and the covariance of a Gaussian random vector, then you can completely specify the probability density function of Gaussian random vector, right. So, when we started talking about these random processes, we said that defining and specifying probability density function can be quite complicated, because you have to talk this probability density function for every time epochs, you have to talk for every argument and so on and so forth, but this probability density function is a much simpler probability density function, just a function of mean and covariance, okay. And that is why these Gaussian processes are easy to handle and deal with. All right. So, let us talk about one more issue in here. So far we have assumed that the inverse of a matrix exists, right. This should exist, and then only the inverse of this covariance matrix will also exist, right, because this probability density function is a function of inverse of a covariance matrix, and if the inverse of a covariance matrix exists, what we also require is that inverse of A should also exist. Remember, the covariance matrix is nothing but A times A transpose. So, the inverse is, as we have already seen, is this thing, all right. So, what we want is for an inverse of this covariance matrix to exist, that the inverse of this matrix A should also exist. What happens if this matrix A is a singular matrix? Okay. So, if A is a singular matrix, that means the determinant of A is 0, and if determinant of A is 0, then the inverse of this matrix will not exist, and in that case the inverse of this covariance matrix will also not exist, and then what would happen to this joint probability density function? Let us see this. And to understand this in slightly more detail, let me first introduce the idea of linearly dependent variables. Okay. So, let us assume that I have two Gaussian random variables. So, x1 is a Gaussian random variable, and let me assume that x2 is 2x1 minus 3, because x2 is a linear function of this random variable x1, this is also going to be a Gaussian random variable. Okay. Now, let me define a random variable z, which is a linear combination of these two random variables. Now, let us substitute the value of x 2 in this equation. We get this, and simplifying this we get now for any values of a and b, you can easily appreciate that z is also going to be a Gaussian random variable, right, because z is nothing but it is a linear function of x 1, and we have seen any linear function of a Gaussian random variable is a Gaussian random variable. So, whatever values of a and b you choose, z is going to be a Gaussian random variable. Okay. So, now the question is, are these x 1 and x 2 jointly Gaussian random variables? The answer is obviously yes. Why are these jointly Gaussian random variables? Because any linear combination of x 1 and x 2 gives us a Gaussian random variable. Okay. So, now if we look at again these x 1 and x 2, after having understood that these are jointly Gaussian random variables, what kind of random variables are these x 1 and x 2? For example, if x 1 takes in a numerical value small x 1, we know for sure that x 2 will take a numerical value 2 x 1 minus 3, because x 2 is nothing but it is a linear function of x 1, it is a deterministic function of x 1. Thus, if x 1 takes in a numerical value x 1 small x 1, random variable x 2 will take in a numerical value 2 x 1 minus 3, and thus if I know what value random variable x 1 has taken, I can completely tell you the value that random variable x 2 will take, and these kind of random variables are referred to as linearly dependent random variables. Okay. So, x 1 and x 2 are linearly dependent random variables. So, x 2 is a deterministic, it is a linear function of x 1, so linearly dependent on x 1. Specifying x 1 will tell me everything about x 2. Okay. For example, if someone says random variable x 1 has taken a numerical value x 1, we know for sure that this random variable x 2 would take in a numerical value 2 x 1 minus 3, and thus the probability density in this 2 dimension case will lie along a line, is not it? The whole probability density in this 2 dimensional case just collapses to a single line, and in this case thus the joint probability density function is not defined. Okay. Let us see why. So, remember that the joint probability density function of 2 random variables is what? Probability divided by unit area. In 2 dimension it is divided by area, and what is the area of a line? Area of a line is 0. So, the joint probability density function is nothing but probability upon 0, and this is going to be infinite. Thus, we see what happens is, if 2 random variables are linearly dependent random variables, the probability density function collapses to a line, and thus what we see is that the joint probability density function will not be defined until and unless you are willing to allow impulses and delta functions. Okay. We are not willing to take that route because there is lot of notational mess that will be introduced. We want to keep things simple. Okay. So, what we do now? So, how to get rid of this problem? So, what is the solution? Okay. What is the solution if we have bunch of random variables which are linearly dependent? If we have bunch of random variables which are linearly dependent, we have seen that the probability density function would not be defined. Okay. You can also think it in just one more way. So, we know that the area is, in this case it will be delta square times mod of determinant of A, right. We have seen once you go from one space to second space, this is what the area is, and we have seen that the area is 0. If the area is 0, determinant of A would be 0, and determinant of A would be 0, that means A is a singular matrix, its inverse does not exist. Okay. So, we are telling you the same thing in a different way, right. So, what is the solution? Let us try to look at the solution. So, let us assume that I have m random variables. So, here I am assuming that these x1, x2, xm are continuous random variables, and when I say probability that x1 is equal to small x1, x2 equals to small x2 and xm equals to small xm, I simply mean that these random variables are taking values around their corresponding numerical values. So, namely x1 is taking a value around small x1, x2 is taking a value around small x2, and so on and so forth. Now, let me assume that x2 and x1 are linearly dependent. Okay. Rest, let us assume that they are linearly independent. So, once you want to talk about the probability of random variable x1 taking in a value small x1, x2 taking in a value x2, xm taking in a value xm, this probability will be 0 if x2 is not 2 x1 minus 3. Remember, we are assuming as before that x2 is 2 x1 minus 3. So, if random variable x1 has taken in a value x1, random variable x2 has to take a value 2 x1 minus 3, it cannot take any other value. So, if x2 is not same as 2 x1 minus 3, then this probability is going to be 0, because these two events cannot happen at the same time. So, we know easily how to calculate this probability if x2 is not same as 2 x1 minus 3. What happens if x2 is 2 x1 minus 3? What happens then? If x2 is 2 x1 minus 3, probability of x taking in a value x1 and x2 taking in a value x2, where x2 is 2 x1 minus 3, and xm taking in a value xm is nothing but probability of x taking in a value x1, x3 taking in a value x3, and xm taking in a value xm. So, what I am saying is this probability of x2 taking in a value small x2, where x2 is 2 x1 minus 3 is 100% once you know that x has taken in a value, or x1 has taken in a value small x1. Let me put here. Okay. And this probability can be computed from the joint probability density function multiplied by delta m minus 1. See what I have done. What I have done is I have removed this linearly dependent random variable, because I know that once this event has happened, this event would automatically happen if x2 is 2 x1 minus 3. These probabilities are same. If I am interested in finding the probability for this event, this could be simply found from the joint probability density function of random variables x1, x3 and xm and multiplying it with the volume of that space, because now only I have m minus 1 random variables, because I have chucked out this random variable x2. The dimension of my space has reduced from m to m minus 1, and this joint probability density function is also specified over a lower dimensional space, and this probability density function will be defined because now there are no linearly independent random variables here anymore. Whatever random variables were dependent, I have removed them, because whether you include this or not, the probabilities will remain unchanged. So, this event has the same probability as this event for x2 taking in a value to x1 minus 3. Okay. So, what we are doing is we are defining this probability density function over a lower dimensional space. When we are doing this, we are checking out all linearly dependent random variables, because of which this probability density function in original dimension was not defined. And now we have this probability density function, which will be always defined, because this is only consisting of random variables which are linearly independent, and we are multiplying it with the volume of lower dimensional space. Okay. So, in short, this is what we are doing. We were having a bunch of random variables. These bunch of random variables might have some random variables which are linearly dependent. We check out those random variables, the linearly dependent one, and then we have a probability density function, a joint probability density function, which we can get defined over a lower dimensional space, which only consists of random variables which are linearly independent, and we can get rid of this issue. Okay. So, one question that is of interest is linearly dependent random variables are also statistically dependent? And the answer is obviously yes, because what is linear dependence? Linear dependence means that one random variable is a deterministic function of another random variable. So, if you know this random variable, you know everything about this random variable. So, it is a completely deterministic dependence. When we are talking about statistical dependence, it simply means that once you know about a random variable, so for example, if two random variables x and y are statistically dependent, it simply means that if you are observing y, your information about x has improved, but you would not know everything about x. Okay. So, if these are linearly dependent, that means you know everything about the other random variable, then these two random variables will also be statistically dependent, right. But if these random variables are statistically dependent, they need not be linearly dependent. The statistical dependence is weak dependence, right. It is a probabilistic dependence, whereas linear dependence is a completely deterministic dependence. So, statistical dependence does not imply linear dependence, but linear dependence imply statistical dependence. Okay, let us conclude this issue by relooking the probability density function of random vector z. So, let us use this one. So, we have already derived the probability density or joint probability density function of random vector z, and this is also a tool to define Gaussian random vector. So, what we are saying is, if a random vector has such a joint probability density function, then that random vector is a Gaussian random vector. Okay. If it is a Gaussian random vector, this should be the probability density function. If this is the probability density function or joint probability density function of that random vector, then that random vector involved is a Gaussian random vector. So, this is third way in which we can talk about Gaussian random vector or jointly Gaussian random variables. Once we have said that this is a Gaussian random vector, and then we can also say that its element should be jointly Gaussian random variables. Okay. So, this is a third definition of jointly Gaussian random variables. That means, jointly Gaussian random variables has such a probability density function. Okay. So, let us now try to look at the last issue, and this issue is trying to understand this expression little better in some spatial cases. I am rewriting this time and again, so that it gets imprinted in your head. So, this is the expression, and remember that these z are small z's, right, they denote the numerical values rather than the vector itself. Okay. Now, let us try to ask ourselves a question: what happens if the elements of z, that means z1, z2, zn, so these z1, z2, zn are random variables. What happens if these random variables are uncorrelated? What happens to this probability density function? So, this is what we are trying to discuss and see, okay? And we will end up with very interesting result. So, let us start with the premises that these z1, z2 and zn are uncorrelated. And to begin thinking about this, let us just start taking two random variables z1 and z2, and let us see what happens if z1 and z2 are uncorrelated. Now, if these two random variables are uncorrelated, their covariance must be 0. Okay. So, covariance of z1 and z2 must be 0 if z1 and z2 are uncorrelated, right. This is how we define uncorrelated random variables. So, what is z1? z1 we know is a11 times w1 plus a12 times w2 and so on and so forth, a1m times wm, and z2 is a21 times w1 plus a22 times w2 plus a2m wm. Okay. Now, substituting these expansions of z1 and z2 in this equation, we get all right. Now, we know that covariance is a bilinear operation. So, we can multiply these terms with these terms and there will be some cross terms. Okay. I will not derive this completely, I will leave it to you to see that once you multiply these cross terms and you take the expectation after multiplying these cross terms, what we will get is a flat 0, because w1 and w2 are independent, right, and they are with 0 mean, right. So, expected value, let me write a11 w1 into a22 w2 would be 0, right, because they are independent and they are with 0 mean. We have done it several times, and now I request you to do it yourself and think that all these cross terms will vanish. Okay. So, finally, what we will have is summation a1i a2i variance of wi, where I goes from 1 to m. Okay. just try to prove it yourself, it should be simple and easy. Furthermore, what we know is that these random variables are also normal random variables, that means their variance is 1. So, from this we can say that covariance of Z1 and Z2 is nothing but summation I going from 1 to m A1I times A2I, assuming that this is 1. And we know that if these two random variables have to be uncorrelated, this has to be 0, all right. So, let us see under which condition this will be 0, and for that let us assume that I have a matrix A, and this matrix A consists of m rows, and let us say that I am interested in the inner product of row 1 with row 2. And what is the inner product of row 1 with row 2? It can be obtained by multiplying the elements of row 1 with the corresponding elements of row 2 and then summing this up. So, the inner product of row 1 with row 2 is exactly the same thing as we have derived before. Of course, you can have conjugate if these elements are complex, but we are assuming everything to be real and thus there are no conjugates and so on and so forth. So, what we are saying is if these two random variables Z1 and Z2 have to be uncorrelated, this quantity has to be 0, that means the inner product of row 1 with row 2 has to be 0. Okay. And this simply means that for the random variables to be uncorrelated, row 1 has to be orthogonal to row 2. And if you want random variables Z1, Z2 and Zn to be uncorrelated with each other, what you simply require is that these rows should be orthogonal to each other. And you know that if A is an orthogonal matrix, then rows as well as columns are orthogonal to each other. Thus, if you have this linear transformation Z is A times W, and if you assume A to be orthogonal, then what you ensure is that these elements of Z, which are Z1, Z2 and Zn or Zm, they are uncorrelated. Okay. Now, let us see what happens to this joint probability density function if these elements are uncorrelated. Okay. So, let us now assume that these are uncorrelated and let us see what happens to the joint PDF. And joint PDF depends upon the covariance matrix. So, let us see what happens to the covariance matrix. And what was the covariance matrix? It is the expected value of Z times Z transpose. And so, this is expected value of Z. What is Z? Remember, by notation we are assuming the vectors to be column vectors. So, this will be Z, Z transpose will be this, and we have done this several times. This would be Okay. Now, we can pull this expectation operator inside, and we know that expectation of cross terms, for example, Z1 Z2, this would be 0, because we know that these are uncorrelated and we also know that they are with 0 mean. So, expected value of Z1 times Z2 would be 0. So, all these cross terms would vanish. Okay. So, finally, what we have is covariance matrix will be expected value of Z1 square, it will be a diagonal matrix, expected value of Z2 square, expected value of Zm square, and so on and so forth, rest will be 0. Now, let me use a notation to simplify this expression, that expected value of Zi square is sigma I square. Okay. So, we are using this notation to talk about expected value of Zi square, and hence our covariance matrix becomes sigma 1 square, sigma 2 square, sigma m square, right. So, we have to find now the determinant of this kz and kz inverse, right, because joint PDF depends upon that. So, let us do the easy one first. What is determinant of this kz? Determinant of a diagonal matrix, you must have seen, is nothing but it is the product of diagonal elements. So, determinant of kz will be nothing but sigma square times sigma 2 square to sigma m square. This was easy. Was an inverse of a diagonal matrix. Inverse of a diagonal matrix is also easy. This is obtained by the reciprocal of diagonal elements. So, this will be 1 by sigma 1 square, 1 by sigma 2 square, 1 by sigma m square, and everything else will remain 0. So, this is how you take the inverse of a diagonal matrix. Let us now see what is Z transpose kz inverse times Z. I would not derive this, I leave the derivation to you because it is quite straightforward. This will be Z1 square by sigma 1 square plus Z2 square by sigma 2 square, Zm square by sigma m square. So, now is the time to plug these things. So, let us say this is expression number 1 and let us say this is expression number 2 in the expression of joint PDF. So, we will have 1 by 2 pi raised to m, determinant of kz will be sigma 1 square, sigma 2 square up to sigma m square, and then I will have exponential minus z1 square by sigma 1 square. So, all these z's are small z's. Okay. Whole divided by 2, and what you can see is that you can conveniently express this joint PDF like this. So, this denotes that I am interested in taking the product of the terms. So, I will have this is I, so the joint probability density function of a Gaussian random vector z, when the elements of this random vector z are uncorrelated, is computed to be like this. And if you see this carefully, what happens? There is something interesting going on here. First thing that you realize that this is the marginal PDF of Gaussian random variable Z I. And what we are now saying is the joint PDF is nothing but it is the product of marginal PDFs of the involved random variables. And we know when this happens. When does the joint PDF is simply the product of marginal PDF? This happens when the underlying random variables are statistically independent. And thus we see something beautiful has happened, that these random variables are statistically independent random variables. So, we can say from this that Z1, Z2 and Zm are statistically independent random variables. So, this is a proof that when these random variables are jointly Gaussian random variables, and if these random variables are also uncorrelated, then these random variables are also statistically independent. That means uncorrelated jointly Gaussian random variables are also always statistically independent. Remember, this was not true in general. Uncorrelated random variables does not imply statistical independence, but if these uncorrelated random variables are also jointly Gaussian random variables, then uncorrelatedness implies statistical independence, and this is something important. Let us try to finish this lecture. Let me make a small table which might help you in clearing out some confusions if they are remaining. So, what we are saying is if Z1, Z2 and Zm are jointly Gaussian random variables, they might be linearly dependent, is not it? If these are linearly dependent, it also means that they are correlated, and the correlation coefficient can be 1 or minus 1. It also means that they are statistically dependent. Now, the case 2, these random variables can be linearly independent. If these are linearly independent, they might be correlated, where the correlation coefficient will lie between minus 1 and 1, but it cannot be minus 1 or 1 or 0. If they are correlated, they are also statistically dependent. They can be uncorrelated, and then the correlation coefficient is 0, and this implies that they are also statistically independent. Okay. So, this brings us to the conclusion of today's lecture. In today's lecture, we have covered lot of important concepts. We have derived the joint probability density function of a Gaussian random vector, and we have seen there that the joint probability density function of a Gaussian random vector is only a function of mean and covariance matrix. We have further seen that it might happen that the jointly Gaussian random variables involved are linearly dependent, and then the best way to sort out that issue is to consider the bunch of random variables which are linearly independent and define the probability density function over a lower dimensional space. The third thing that we have seen is that if we take the A to be an orthogonal matrix, then the elements of Z will be uncorrelated, and if the elements of Z are uncorrelated, it will also guarantee that these random variables are statistically independent. Thus, uncorrelated jointly Gaussian random variables are always statistically independent. From next lecture, we will see some more interesting things in the context of random processes. We will see what happens when this random process pass through linear time invariant systems or digital communication systems. Thank you.